Alright, ladies and gentlemen, boys and girls, children of all ages, Physics Rocks It's True presents its first ever double-headed live stream lesson. We are going to start for the first half hour tonight with the Year 12 content, and that's going to be alien life, the search for extraterrestrial intelligence, and the end of the universe as we know it. Spoiler alert, it's all relatively depressing. Then we will transition at about 8:45. We're going to go to the Year 11 stuff, where we're going to do motion time graphs. So if you're resitting a module, hang around for that. That's a useful one. And then after that, we're going to take a look at pressure, which is brand new for the Year 11 course for those of you who are sitting it for the first time this year. So, without further ado, let's get into it. We're going to talk about the potential ends of the universe first, because that really informs our search for extraterrestrial life. So, in the last episode, we finished off with this concept that the universe is continually expanding. And we know that because if we look at other galaxies within, so these represent galaxies, if we look at other galaxies around us, then the galaxies are moving further away from each other. Not necessarily just from us, but from each other, in a manner consistent with that of an explosion, which lends credence to the concept of a Big Bang event at some point. Now, it gets a little bit worse in that the further away the galaxy is, the faster it appears to be traveling. Okay, so, and again, that's kind of consistent with what you would expect from an explosion, because objects near where that explosion event happened will be traveling slower than objects that are far away. Think about in a normal explosion event, very light stuff ends up fired a long way and goes very, very fast. Heavier stuff kind of coalesces around the middle. Not that the universe has a middle, and we discussed that last time, that even if it did have a middle, we wouldn't be able to appreciate where that was at all. So, we end up in a set of scenarios. The only force that we have to counteract this this explosive force is gravity pulling things back together. Right now, so far, the universe is about 14 billion years old, and it hasn't stopped that since. Okay, so we haven't managed to stop our universe expanding. So we've got a few options in terms of what can happen here. So let's imagine our universe is an expanding kind of ball going out like that there, though more a sphere. Okay, with the edge of the universe, if such a thing even exists, somewhere around here. Now, as the universe then expands, gravity is attempting to prevent that expansion. Okay, simply because of the fact that all the mass of the universe is inside the sphere. It's probably best if we fill this sphere in. So let's get a fill color, and let's make it nice universe, kind of dark blue going on here. So as the universe expands, the stuff is still contained within that sphere. Okay, so at any given time, gravity is going to be trying to stop that expansion because there's nothing out on the edges here, gravitationally speaking anyway, that is trying to pull it further out. Okay, so it's just it's inertia from that Big Bang event. Right, so let's bring that back to here. So option one is that the universe expands out like this, and at some point gravity is sufficient that any amount of velocity outwards is then balanced by a force pulling it back inwards. The universe will then stop expanding. Now, nothing sits still for long. If it stops expanding, then what will happen then is, because the only force is still inwards, then the object will change speed in the direction of the force, so it will begin to contract. And it will continue to do so at an ever-increasing rate because it's accelerating. It's a force, so it's going to get faster and faster and faster and faster and faster and faster and faster until it ends up back at a very small point again. Now, this runs us to two possible endings, and there are the two endings that we want to properly discuss because the two endings you have to know about. One is called the Big Crunch. Okay, as the name suggests, what happens is all the mass ends up back in a small space. Okay. That then, nothing further happens to that. It remains in that space. It forms a super giant black hole because with that amount of mass in one spot, even light's not getting out. Okay, so even if light is being produced, it's definitely not getting out for any external observer to view. And because gravity is so strong, at that stage we have all motion stops. Life ends, obviously, because you're inside a black hole, and the universe, for all intents and purposes, ends. Because a universe that does not have life in it is not observable. Okay, so even if that black hole continues to exist, no one will ever observe that black hole, and therefore it may as well not exist. Okay, not being able to be observed is indistinguishable from being non-existent. All right, so that's option one. Option one is the universe ends as a big crunch, and that's reasonably depressing. Everything gets crushed, dies, everything disappears, and that's the end of matters. All right. Option two is exactly the same as the big crunch, except with one difference. Okay, it is that everything ends up back in a small space again. So all mass, all mans. Hopefully that's not a Freudian slip. All mass ends up back in a small space. Okay, but it doesn't remain in that space. What happens then is it forms a second singularity. Okay, well, remember we said a singularity was what the Big Bang was in the first place. Okay, it was all the mass and all the energy of the universe crushed into a point about the size of a pinhead. Okay, so it forms a second singularity. If you've got a singularity, that's not a stable situation to be in. It's not energetically in any way stable. So that leads to a second Big Bang event. All right. And the universe begins again. It's kind of like setting the reset button. Now, it does have this slight problem with all the mass ends up back in a small space, which again means that at this point, all life ends. Right? Because you're not going to escape this, because the key word here is all the mass ends up back in a small space, and that includes you. That includes you. So if you end up back in a small space and you end up inside a singularity, that's game over, I'm afraid. So again, we have all life in the universe ends. Sorry about that. But the good news is that all the energy, all the mass, and all the stuff that makes you up ends up fired back into the universe in a recycling event. And this is called the Big Bounce theory. Now, whilst that seems just as depressing as the Big Crunch, this could be interesting, because if this means that the universe expands and contracts and expands and contracts and expands and contracts and is somewhat destined to do this forever, there's no reason to suggest that we are the very first incarnation of the universe, that we may in fact be the infiniteth number of the universe, because this is a system that's not going to stop. It's a bit like it's going to keep going round and round and round and round, with time expanding along with space, and it'll go round in a nice big loop event. And if you take a look at this circle, you would be hard pressed to find the start of that circle. Any point is the start of that circle, and any point is the end of that circle. I'm losing a couple of people in chat, that's grand. So if you end up on the end point of that circle, good luck to you, you're not going to find that. Which means that this is kind of an infinitely recycling thing, and we could be, the first, the last, the 75 millionth, whatever. That's kind of nice if you're a fan of the concept of reincarnation, because if you have an infinite number of times that you can go round and round and round and round a loop, and you accept that you are simply the product of lots of atoms being stuck together that makes you, as a matter of probability, those atoms will probably end up coming back together in roughly the same arrangement, making you again. Now, of course, you'll not remember anything from the past, because the structures that make you remember stuff aren't well understood, but you might exist again. Though you won't remember it, and it probably won't be you, and it mightn't have your consciousness, and even if it did, it doesn't have your memories, so kind of what's the point? But it is at least somewhat heartening that humanity might live again, though it may take billions upon billions of cycles of this universe, which is nice. Unfortunately, though, neither of these two theories appears to be correct. Right? Simply because of this, they all depend on the idea that as the universe expands, it will eventually stop expanding. And that would require it to go outwards, slow down, stop, and come back in. And our current observation of the universe doesn't support that. Okay? Our current observations of the universe, as I said at the start, support the idea that if the outer bits of the universe are expanding faster than the inner parts of the universe, then it makes logical sense that as the universe gets bigger, those outer bits are going to get faster again. Okay, something is blowing the universe up, a bit like a balloon, and we're not quite sure what it is, though scientists tend to call it dark energy. And there's a Nobel Prize probably on offer here for anybody who can adequately define what it is, where it is, and how it works. In fact, there's no probably about it. There is a Nobel Prize up for this one. So if you're feeling ambitious over the next few days, have a crack at that problem. Your problem with this, though, is that the universe continues to expand. And the primary issue with that is, and we'll just take this onto a new page, is that imagine that I have a limited amount of paint in which I can shade this circle in. Okay, so let's take a little highlighter pen and shade this in. Okay, and let's imagine that I have that much ink to try and fill this circle. That's it. That's energy. That's the amount of energy the universe has to fill it. If I make the circle bigger and attempt to use the same amount of energy yet still fill this sphere, I sort of end up spreading it out a bit more. And as it gets bigger and bigger and bigger and bigger, this energy gets more and more and more and more and more dilute. It gets more spread out. This means that there isn't energy available for things like heat. There isn't energy available for things like nuclear fusion. There isn't energy available for things like movement. All the energy ends up stored as gravitational potential energy. And at some point, all of the energy in the universe will be gravitational potential energy. Now, if that happens, then logically, whatever heat energy we had in the universe goes towards zero. You've got a set amount of energy. If it's all gravitational potential energy, none of it can be heat. So as a result, then, the universe expands forever. So universe expands forever. Okay, but at a point before forever, basically, all energy becomes potential energy. Okay. Temperature falls, temperature falls to absolute zero. So that is the lowest possible temperature. All motion in particles stops, everything dies. Okay, all the stars go out because there's no heat energy, there's no light energy. So the stars wink out one by one by one by one by one. All the particles get so far apart they can't do anything, and the universe ends. It doesn't actually cease to exist, it remains in place. But again, you have the problem with once everything dies, there is no possible way in the future that anything is going to evolve into being to observe the universe and figure out how it works. So then it may as well not exist. And this is called the Big Freeze. And rather unfortunately, this appears to be what's going to happen. Now, the good news is that our sun will expand and engulf our inner planets and end our civilization long before that. And even if it doesn't, other catastrophic events will happen that are going to wipe out the human species. But even if we could survive those events, it does appear that at some point in the future, the universe will end, and there's nothing we can do about it. So we have a time limit on how long we're going to exist. It's not so good, but we're just going to have to deal with it. Right, so that's the end of the universe covered. But let's be honest, the trailer for this is pretty clickbaity. We're here to talk about alien life. Okay, so at the moment, the universe can support life. We know that because we're here. So what are the chances of our little globe here with our lovely blue planet, and we're going to get A little blue going on here, but we don't want it to look like the universe, so we'll break out the old gradient fill, everybody's favourite, put a bit of green in there. Right, so we've got our lovely Earth here with us happily standing astride on it as the dominant species. Technologically advanced, very intelligent, capable of mastering our environment and taking our first tentative steps out into the cold dark of space. But we're 14.5 billion years late to the party. The universe has been going on for a long time. So what is the chance that somewhere in the faraway distant reaches of the galaxy that there is something standing on a planet having worked all this out before with his little tentacles and his little singular eye and lots of hands? What's the chances that it's looking at us going, aren't they cute? Well, let's have a think about that. What would have to happen? There's quite a lot of things that have to happen in order for you to become a dominant, civilized, intelligent species. First of all, you have to form a planet that is capable of supporting life. Right, so you have to have a star system form with enough stuff left over to form a planet that will orbit around it in such a way that it can support life. Now, things that will support life, as far as we know it, probably requires water, right, or some other solution, or some solvent. The reason that we're so hung up on water is in order to form life, what you need a lot of kind of test chemical reactions going on. You need chemicals to bump into each other constantly and react with each other constantly, running all the possible combinations that you can get of chemicals until they hit on that perfect kind of combination of proteins that start to self-replicate. And that's a game of chance. And water allows you to play that game of chance. If you have all the ingredients for life and they're sat on a solid surface, well, they can't move, they've got no legs. So you can't have them interact with each other. Yeah, you can have some wind blowing, but that's not the same. Okay, things interact in liquids a completely different way than they would interact just when they're forced to touch each other. Okay, so we probably want water or some solvent. So that pretty much limits us to taking out all our barren planets straight away. Anything that doesn't have water or some form of liquid on it can just go straight up. Okay, then you have the actual probability of life happening. That needs to happen. Okay, so life actually needs to happen, and that's a pretty low. We reckon that's a pretty low probability event. Like, we don't see life just pop into existence all the time. So as far as we're concerned, we don't see it in our solar system, we don't see it in any of our nearby stars. The likelihood of it just happening is pretty slim. Though one of the big focuses now on going to places, on sending probes to Mars and sending probes to the deeper outer solar systems and places that have water, is to go and have a look at, well, maybe there's bacterial life, maybe there's some very, very simple life. And if that was to be the case within our solar system, then life happens might actually be quite a probabilistic event. If it happens multiple times in our solar system, then we could maybe make the argument that this is not a low probability event. Right? Then we have to have life evolves intelligence. Now, that seems like a no-brainer. Like, if you've got life, surely something clever is going to evolve. But we've been around a long time on this planet. Like, life's been around for a good while on this planet, and it's taken to now for intelligence to be a thing that's actually valued for survival. That the human species is one of the first that has, proper problem-solving skills as part of its evolutionary tool set that allows it to dominate the environment around it. Because building a big brain is energy intensive. It's difficult to do that. And it costs a lot. It costs a lot of energy. You need a lot of food to run it. So you might actually be better off being stupid, but able to get enough food to keep you going, rather than being very, very clever and just starving to death because this brain demands so much energy of you. So life evolving intelligence is a thing. Then it has to not destroy itself or get destroyed. Now, that could be good or bad. Like, for example, when the dinosaurs dominated our planet, there was absolutely no way that the tiny little rodent-like mammals that ended up as us were ever going to dominate the landscape in the face of a T-Rex. So we had to wait for the large-scale extinction event at the end of the Cretaceous period to kill off all of our competitors in order for us to scurry around in the dark for a long time to become the dominant species. Now, it may be that life has evolved on other planets and it's evolved to a stage of like dinosaur level dominance. It's big, it's dangerous, it's running around killing all sorts of stuff, but it has no need to evolve intelligence and problem solving skills. And then, even if it did, that it gets to a technological state where it develops like nuclear weapons and then wipes itself out. Well, whoops. But if you get to the stage, you're almost certainly going to be a competitive animal. Almost certainly, because that's how evolution works. That the best and brightest and the things that can kill the most things dominate. So you're going to have whatever it is being a natural born killer. We're one of the most dangerous things that we know of. And our creativity for killing each other is what drives us forwards almost. Right, so you have this problem that it might be that intelligent life evolves but then just blows itself up, and we're the exception. That we're the ones that managed to not have the Cuban Missile Crisis blow us up. That we're the ones that wouldn't possibly allow a crackpot in North Korea to develop nuclear weapons and point them at everybody around them. That would be just stupid, wouldn't it? So then we would have to get to that stage. And the problem here is that we have absolutely no idea what the probability of any of these things are. It could be that life happens is really probable. It could be that it's really improbable. It could be that we're unique in the life happening thing. We have a data point of 1. We know it happened, but that's it. We could be rolling a 1 billion sided dice. Actually, that would be quite good even if it was a billion sided dice, and we just happened to get a 4, and that was the one that was required for us. And rolling that dice again, you'd be doing it a long time before life happens again. And then for life evolving intelligence could be another billion sided dice that we have to roll and get a 3 as well as a 4 for life happens. Okay, and that probability goes down because when you add probabilities together, we have we end up multiplying them and get much smaller numbers. And then not destroying itself or getting destroyed, again, we don't know what the probability of that is. We know we've had a couple of major extinction events on our planet alone, so our data point there is planets get hit by stuff. That's bad news. So the actual odds of life existing in the universe are unknown. What we do know though is that the universe is very, very big. Okay? It is very, very big. Like so big, if I was to put a number on the screen, the number means nothing in terms of the number of planets that we can possibly be dealing with here. So that gives us hope that even if this probability is infinitesimally small, we have a very, very, very large number of chances to play this game, so we might end up with life everywhere. Grand. So let's work on the principle that there might be life. How would we go about determining whether or not it was out there and whether or not we were alone? And the game is this, that if you make certain assumptions about what intelligent life will look like, you're probably going to look at it's going to develop large-scale cooperation. That's how you become dominant on a planet. Okay, that's how any species becomes particularly dominant, that they end up cooperating well. The species that's going to become most dominant is going to be the one that does it best and can probably do it on a global scale. In order to be communicative on a global scale, you're going to have to develop communication-based technology. Communication-based technology would want to be as fast as it humanly, or as it alienly could be, and that means you're going to take advantage of the universe's natural speed limit, which is light. Now, that means you're going to develop a communication system based on light speed travel. And that leads you straight to the electromagnetic spectrum. Okay, you want something that's not going to have the limitations of not bending around corners. You're going to want something that bounces relatively easily. You're going to want something that's kind of low energy for output. So you're going to be led somewhere towards microwaves and radio waves in much the same way that we are with our TV signals and our mobile phone signals that we use for our own communication. So this is what the search for extraterrestrial intelligence is currently doing. What they do is they look at the waves that are coming from the background radiation in space. And if you're to put it on a CRO, it looks a bit like this. Okay, it's all jaggedy, mental. It doesn't go back in itself, but I'm really bad at drawing. But it's completely random. Okay, there's nothing at all of any form of note there. It's just static hiss, the leftover glow from the Big Bang. And what we're looking for is something that looks like this inside the background radiation. Okay, something that looks far too smooth to be created by a naturally occurring phenomenon, something that has been generated, something that has been purpose built for the purposes of communication. And if we can find that, we might have some form of evidence that an intelligent life form exists out there. Okay, so the Search for Extraterrestrial Intelligence, or SETI, as it's known, does this. Okay, that they take radio telescopes, which are basically, they're like telescopes, except instead of using light, they use radio waves. That they look for radio waves. So let's draw ourselves a little radio telescope. Okay, basically like a big satellite dish, and it collects the information from the background radiation in space. So all these waves come rolling into it, and they analyze it. Okay, from point at a certain section of the galaxy, point at a star, and have a little look at what's coming from that. And to date, after decades of trial, we've got nothing. That's not entirely true, actually. We got a weird signal once, but it turned out to be a brand new type of kind of star that was going on, and Nobel Prizes were awarded for it, but not quite as exciting as the prospect of finding extraterrestrial life. So far, the skies are silent. The skies are silent. So there are a couple of reasons for that. Reason one is we might be wrong about our assumptions about what alien life is like, or that they haven't gotten that we are actually the most advanced civilization in the universe ever, and nobody else has developed this. And life could be everywhere, but we are the top of the tree. Or more depressingly, we are alone as the only life in existence. The upside of that is, though, that when asked about this, a SETI scientist said, yes, it's absolutely true that we haven't found anything yet, because the reason we haven't found anything yet is because we've basically gone down to the ocean, put a cup in it, lifted out some water, and concluded that there are no fish in the ocean. The universe is extraordinarily big, and even though we might think that having searched for stuff for 50 years is a long time, if you're looking through a galactic-sized haystack for a needle, then 50 years is not a particularly long time to be doing that for. So the search continues. The other problem is that, of course, even if we did find evidence of alien life, we'd almost certainly not be able to contact it or deal with it in any kind of intelligible way. Remember that our nearest stars are about a light year away, which means that light, and therefore any radio-based transmission or any other transmission, would take at least a year to get to us. And light from other galaxies, we're talking about hundreds of thousands of years. That even if we got a message that says, hello, is anyone there, and we decided to send back, yes, we're here, if they're 100,000 light years away, they sent it 100,000 years ago, we send our message back, that's going to take 100,000 years to get there, and then they're going to go, great, which will take another 100,000 years to get to us. So by the time we receive their second message, 300,000 years will have passed since they sent their first message. And that runs us back to one of our kind of filter problems, which is in 300,000 years, you can get destroyed pretty handily. So even if we could make contact with other species, it's unlikely we're going to be able to form any form of meaningful contact, though we may be able to go, right, they're there, throw them all of our information, so that if it gets back to them and they haven't been destroyed, they will know everything about humanity, and they might reciprocate and tell us everything they know about us, and we could mutually get better and better and better and maybe overcome this light speed problem. The sad thing about it is that we simply don't know. We simply don't know if alien life exists. And as a question as a physicist you get asked a lot of the time. You get asked, do you believe in aliens? And my answer is pretty straightforward. No, I don't believe in aliens, because belief is something that you shouldn't do as a scientist. Belief should be based on confidence in your experimental results, and we don't have any. We don't have any that say there is alien life. We don't have any that say there isn't alien life conclusively. So the correct response is we don't know if there's alien life. And to say you believe in aliens is much the same as saying you believe in fairies. The evidence just isn't there at the moment. And if somebody presented evidence for fairies, you would accept it. Well, you'd be skeptical to start with, but if they presented robust evidence for fairies, you would have no choice but to accept it. And if you presented robust evidence for aliens, you would have no choice but to accept that too. But both fairies and aliens currently fall into the category of has no evidence. So I'm afraid it was a bit of a depressing lesson on this one, that the universe is going to end as a big freeze with everything going cold, dead, dark, and everything dies, and aliens, not sure if they exist or not. The best we can intellectually say is, I don't know. and even if they do exist, the likelihood of us ever meeting them is pretty remote, unless they have technology that actually currently violates our understanding of the laws of physics. And that is 8:45 on that one. Half an hour flew by, for me anyway, on this one. I'm going to take a little 1-minute break, get myself reset for the year 11 lesson coming. Thank you so much for joining me. If you are doing a reset, I recommend you hang around for the next one, and I will see you very, very soon. Okay. Take care, everybody. Alright everybody, we are back for part 2 and we're into our year 11 content. We're going to take a look at motion time graphs, how they work, the rules you require in order to be able to navigate them, and then we're going to take a look at one of our brand new topics on the year 11 spec, which is pressure. So let's get started. Motion time graphs fall into basically 2 categories. In all situations, you're going to end up with a y-axis and an x-axis, and on that x-axis is going to be time. Now that time may be in seconds or hours or minutes or whatever, okay, but it's going to be some unit of time across the bottom. Right. Now up the side we have a couple of options. Option 1 is either distance or displacement. Now don't be afraid about displacement, it's simply distance away from a certain point. So if you see displacement, just think distance away from home, how far you are away from a fixed point. And we'll maybe draw a little house in the bottom corner here to help with the explanation of that later on. All right, now let's draw ourselves a little vehicle in order to demonstrate the point. Okay, so one vehicle. There we go. Graphics quality continues to improve. So what I want to do is I want to tell a story here. I'm not looking for a trend. I'm not looking for some form of universal truth about the movement of this car. What I'm looking to do is describe how it moves over a period of time. So let's take our little car and drive it. Okay, and we drive it this way, and then we drive it back a bit, and then we drive it over here, and maybe we sit still for a while, and then we drive off again. What we might end up with is something along these lines. If we're going to go with distance first, so I'm just going to box out the or displacement. We'll talk about that in a second. So we'll just box that out for now. Okay, so let's take a look at the distance graph for this. That the car starts off, it travels a certain distance, let's say, then it travels a certain distance again, then it maybe stops for a minute, and then it travels a certain distance. All right, so something like this. Okay, now what we want to do here is we want to make some judgments about this. Now, the first thing we notice on a distance graph is that it always goes up. There is no situation in which your distance over a period of time decreases. Your distance just in general is how far you've traveled. So even if you walked away from your house and you walk back, the total distance you've covered never goes down. Okay, if you've walked 100 meters away from your house and you walk 100 meters back, you've walked 200 meters. That's distance. Okay, so what we now want to do is we want to describe what's happening in this graph. Now there are two ways of doing this. Way one, if you're a big fan of just learning stuff, you learn stuff into your brain, then you can just learn the rules for these graphs. I'm not that type of person. I don't recommend it as a thing because when you're memorizing stuff that looks very much the same about things that look very much the same again, then you make mistakes. You're better off actually establishing what's actually going on here. So let's take a look at this section of the graph. Okay, so we'll start with this section here. What can I say about this graph? Now what I'm going to start with is I'm going to start with the phrase as time goes on, because that's always going to happen. Time continues to go on. So we're going to start each of our descriptions with as time goes on. Your brain should do so too. So as time goes on, my distance increases is a good way to put this. But my distance increases could also be done like this or like this. Okay, we can do better than just distance increases. In this case, as time goes on, distance increases in a steady manner. Now the only way in which your distance is going to increase in a steady manner is if you're traveling in a steady manner. And the only way you can travel in a steady manner is to go at a constant speed. And that's what this section of the graph tells you, that this section says constant speed. So what about this second section here? Like this looks like it's doing much the same thing. If we look at this just from here to here, so up in this upward kind of section here, from this time across to this time. What's going on here? Again, we can say as time goes on, my distance is increasing in a steady manner. That remains true. So it remains true that this is also traveling at a constant speed. But again, we can do better. We can say here that in the time interval I've been given, my distance has increased faster than it had before. It took me a reasonable amount of time here to get a relatively small distance, whereas in probably less than the time before I've covered more distance. So I can say that this is constant speed but faster than before. Alright? And then we end up with this interesting point here, which is, I'll just draw a little blue tag across the top of this. In this section here, we have a situation where my distance value on this axis is not changing. My distance refuses to change, so as time goes on, my distance does not change. And the only situation in which that can be true is if I am stationary. So I'm stationary in this situation. So for distance time graphs, we have a couple of situations where we need to recognize. One, that lines that are kind of straight lines and diagonally upwards in any respect represent constant speed. The steeper that line, or to be mathematically technical, the greater the gradient of that line, the faster the object is traveling because it's covering more distance in the same amount of time. And a horizontal line represents distance not changing, and as a result, this object is stationary. Now that is distance time graphs. And basically, they're much the same, in fact, as velocity time graphs. So let's clear out this graph and let's box off distance. And let's go displacement. Now, the only thing a displacement graph is going to look like differently is this, that it can come back down. Because whilst it's not possible for your distance to come down, you've always travelled more meters than you have before. Displacement is how far away you are from the house. So if I go, I'm away, my distance is increasing, and I turn around and come back, my distance is still increasing, but my displacement, my distance away from the house, is permitted to decrease. So again, we've got to run the arguments. What's happening here? In this section, we have our displacement is increasing as time goes on, our displacement is increasing at a steady rate. So again, this is constant speed, but this is constant speed away from the house. Okay, if we've established the positive is away from the house. Now that's a problem because now we have a speed, which is a scalar quantity, with a direction away from the house. So we would be more correct in saying that this is constant velocity because velocity is the vector equivalent of speed. Okay, so we have the constant velocity going on. Now, as far as calculations and stuff go, they're roughly the same thing. The only thing that velocity has is that it has a directional component to it, it has a directional part. Our next section again looks much the same, that we have between here and here, that we have our displacement is increasing steadily again, and is increasing at a greater rate as time goes on than it was before. So again we can say that this is a constant velocity, and again we can say that it is faster than before. And then we come to our little plateau here where the displacement does not change. My distance away from the house does not change. And again, the only way that that can happen is that this object is stationary. Now the interesting bit happens in this last section, so let's clear ourselves a little bit of space to do that. So undo all that. This bit is interesting. What happens here is between these points, to get myself my little line to explain what we're after, so between here and here, as time goes on, displacement decreases. That is that my distance away from my house decreases. So in this way, I can say, again, I'm traveling at a constant velocity, okay, because my line is nice and smooth, nice and straight, nice and steady, but this time we can say that we are traveling backwards or towards the start. And I don't want to put a misconception into you here that you're reversing in any way. Like, it is possible that in the time that you've been stopped, you've turned around and just walked backwards. Like, you don't have to go back to your house by walking backwards. You can turn around and walk there. What we're saying is that this thing is now moving in the opposite direction to what it was doing before. And it is even possible for displacement graphs to go negative, where they go under the axis, because if I've established that my house is 0 and this way is positive, then if I travel to the other side of my house, then I'm now in the negative zone of my little displacement number line. Imagine I had a number line across the bottom here that had the displacement starting at 0 here and running up to infinity over here. Good size text box. So, well, that's the entire positive number line over here. So if I find myself over here, I have to extend my number line back beyond 0, and that makes me in the negative zone. So calculations wise, all we're really interested in doing here is finding the speed or the velocity of this object, because that's the only information that this graph gives me. It doesn't tell me anything about anything else. I can read how far it's gone off by just reading the y-axis. I can read how long it's been going for by reading the x-axis, and I can work out how fast it's going. And how I do that is by using the equation that the average speed is equal to my change in distance divided by the time that takes. Okay, speed equals distance over time, for those of you who like the quick shorthand of that. Ooh, wrong line, we need a fraction here. Speed equals distance over time is what we want here. Now, for those of you who are pretty quick on this, what you'll find is to get the change in distance, I would need to take my initial distance here, or sorry, my final distance that I end up, so somewhere here, and my initial distance here, and then I would divide that by the time taken to get between this distance and this distance. Okay, so all I need to do is read this off. So that's easy in this one. If I wanted to know how fast I was going in this section, I would need to take this distance up here away from the, this distance here away from this distance here, find the difference between those two distances, and work out how long it took to get that. Now, the savvy amongst you will realize that finding the difference between those two is finding the change in this height. And finding the time it takes to do that is working out this length here. And if you have a change in height divided by a change in length over here, then you have a rise over run situation. That you have measured the rise of that graph divided by the run it takes on this, and therefore that is equal to the gradient of the graph, which is exactly what we expected, because what we said was that the steepness of the graph was the speed. So it makes entire sense that the gradient of this graph is going to be the velocity. And it is in terms of actual measurements. It is in terms of maths. Right. Now, getting the unit for our speed is nice and simple. We take the unit of the rise, so let's say that might be in meters, and the unit of the run, that's going to be your x-axis unit, so let's say that's, let's call it minutes for the sake of it, because seconds is too obvious. Then the unit of your speed is going to be the rise unit per the run unit. So therefore, that would end up as meters per minute, which is not a particularly good unit to use, but if you're something like, I don't know, a very slow movie, like a turtle, for example, meters per minute might be a better unit to use for speed rather than meters per second, because that number is going to be very, very small. And that's displacement time graphs or distance time graphs, and that's all there is really to them. The confusion happens, the reason that people find this difficult is that we end up with a second type of graph. And this type of graph looks entirely the same, that we have a speed or velocity graph, which suffer from the same problems as distance time graphs, that one is the scalar version, one is the vector version, and across the bottom we have time again. Now let's draw ourselves a graph that looks remarkably similar to the one that we had before. So we had a little line here, then a steeper line, and then a plateau, and then we had another line that will eventually turn downwards. Now what we want to do here is that we want to take a look at what's going on in this section. Right, so let's start with our kind of given idea that as time goes on in this first section. Okay, so as time goes on, we want to take a look at this. What's happening? As time goes on, the speed of our object is increasing. And more importantly, it is increasing steadily. So what we can say is this is speeding up steadily. And that's okay as an exam answer, believe it or not. Speeding up steadily is fine, though we want to be a little bit more suave about such things. So we're going to say that this thing is accelerating. And it always helps to be suave if you can spell the stuff that you're teaching. So we're going to say it's accelerating, and we're going to say it's accelerating steadily. Never, ever, ever say that an object is accelerating at a constant speed. That is a contradiction in terms, and it appears in exam questions and exam answers all the time. As an examiner, I see this, that people say this is accelerating at a steady speed. You can't accelerate at a steady speed. If you're doing a steady speed, you're not accelerating. You accelerate steadily. Okay? That you're getting faster, but you're getting faster in a nice, controlled, simple way. Okay? Happy with that? So we're speeding up steadily, or we're accelerating steadily. In the second section, we're in much the same situation as we were before, that we have, as time goes on, again we have this object is increasing in speed in a steady manner. So this one is accelerating steadily, but we can do better. Now this is where the confusion comes. You really, really want to say that it's accelerating faster than it was before. But faster, slower, and at constant speed are speed concepts. So we say this is accelerating steadily, but at a greater rate. Okay, so in distance time graphs, it's okay to say that you're traveling at a constant speed, you're going faster, you're going slower. But in acceleration graphs, we don't say that, because we are always getting faster. We say we're accelerating steadily, but at a greater rate. Now here's where we get you. If we're an examiner, this is coming. Okay, I'm setting this question as an examiner all the time. What's happening here? As time goes on, the speed is not changing. And if your speed is not changing, there are one of two possible things you're doing. You either stopped or you're traveling at a constant speed. Now in this case, we are traveling at constant speed. And I happen to know that because the speed value here is not 0. 0's down here. The only way on a speed time graph that you can possibly be stopped is if your line is along the x-axis. And that way, as time goes on, your speed is not changing, and critically, your speed is equal to 0. Right, so what can we work out from this graph? This is where life becomes super interesting. Because we've established that we're speeding up steadily and we're accelerating steadily, we should be able to calculate this acceleration because it seems to be in some way related to the gradient of this graph. So let's take a look at our acceleration equation, that a is equal to v take u over t. Now, for those of you who haven't been introduced to this style of equation, v is the final velocity and u is the initial velocity, or this top line just reads change in velocity over time taken. Okay, so let's take a look at our kind of second one here again. If I wanted to find out how much it's accelerating in this region here, what we would do here is we would go and would look across and would get the value of speed here, and that would be v. And then we'll go down here and would read off this value with the little lines, and that would be u. And I would have those two values. And then I would have to find the time it takes to get from u to v, which I'd just draw lines down here, and I would measure this width here. Okay, I'd measure the time across there, and that way. And I'd just perform this calculation, a equals v minus u over t. But again, for those of you who are quite sophisticated at maths, you will recognize that v minus u again is the rise of this graph, and the time that it takes to do that is again the run of that graph, and we find ourselves in this situation once more, that the gradient of the graph, the rise over the run, is equal to the acceleration. What is wrong with me? The L key is not working on my keyboard. I'm blaming my keyboard. It's not my keyboard, it's my brain. Okay, so the gradient is equal to the acceleration in this case. And this all looks very, very similar, and we're happy with that. But the cool thing here now is that we can actually work out how far this thing has gone. Okay, and how we do that is we make use of an equation that says this, that the distance traveled is equal to your average speed, try that again, multiplied by your time, which again is a rearrangement of speed equals distance over time. The distance traveled equals average speed over time. It's this average bit though that we have to be very careful of, that because this thing's not traveling at a steady speed, we can't just pick a number. We do have to find the average. So the distance traveled, because we're speeding up steadily, the average is simply the midpoint between our values of v up here, which I'll pop back in, and u down here. Okay, the average value of those two is whatever value is slap bang in the middle. Makes sense. The average of any two numbers is what's slap bang in the middle of the two of them. So we can say that the average value of this speed is going to be v plus u divided by 2. This is how you get the average of anything. Okay, add them together, divide by the number they are. We have two speeds, so we add them together and divide them by 2. That gives me my average speed, and then all I have to do after that is multiply it by the time, which you can do. Do that as a calculation. Do distance traveled equals v plus u over 2 times time. It's a useful equation to have. It's one of Newton's equations of motion, so it's worthwhile knowing, especially if you're doing further maths this year. But it's not entirely necessary, because by finding the average speed and then multiplying it by time, what you've actually done is you've calculated the area enclosed by this graph. And that's super useful. That's super useful, because what I can do now is, if I'm asked to calculate the entire distance traveled by this whole thing, that becomes a real pain. It's a real difficulty, because I have to do lots of individual calculations. But what I can say is that the distance traveled is equal to the area between the line and x-axis. Now, some people will hear this as the distance traveled is equal to the area under the graph. I don't like that, because if your graph goes negative, you're done. What's under the graph? Is that downwards in the y direction, or is it between the line and the x-axis? Is much more technically correct. And if I want to find out how far this thing goes, all I have to do is break this whole system up into a series of nice, regular geometric shapes that I can deal with the end point being the vertical stop at the end. And I break it up into triangles and rectangles. And if I calculate this triangle using half the base times the height, and I pop that number in, and then I measure this rectangle with just using base times height, and then I measure this triangle using half the base times the height. Be very careful that the height of this triangle is this line, not the whole distance up on the y-axis. And then I do this rectangle and this rectangle, and I put the numbers in. So as I'm going, I'm putting in 100 here and 100 here, and 35 up here, and just being really careful with it. I just add them up at the end. Add them up at the end, and I will get the total distance traveled. If I only want the distance traveled, up until, say, this little red line here that I've got my mouse over, then I add up all the areas in the time before that, and I don't bother with these ones at the end. I just don't bother calculating that. Now, the examination mark schemes are very clear on this, that they give you a mark for attempting to calculate the area under the graph, and any attempt to do any form of weird speed distance time calculation that's not an average speed time graph just gets wrong physics and marked as 0. There's no attempt at giving you marks for working out. Alright, so be careful with this. So the key bit of advice I will give you on motion time graphs is this. The first thing you need to look for when you see a motion graph is what is going on here. If it's speed or velocity, we're looking at these rules. Acceleration is your gradient. You accelerate at a greater rate. You avoid the word speed entirely. And the gradient of that graph is your acceleration, and the distance traveled is the area under the graph, or the area between the line and the x-axis, excuse me. If, however, you see the words distance or displacement, you're in this situation. You're in the situation where your line means speed, and the steeper that line is, the faster your speed is. And the area under the graph, or the area between the line and the x-axis, means nothing. Means nothing. Alright? So we've gone a little bit over time and explained that, but most people find that a difficult concept to get on with. And it's a good job that pressure isn't exactly the world's most difficult concept when it comes to actually explaining it. Pressure is the stiletto heel problem, that you have a choice. You can get stood on by a reasonably rotund lady in stiletto heels, or rotund man, I suppose, whatever floats your boat. You can get stood on them with stiletto heels, and I had that happen to me last week, and it was not pleasant. Or you can drop 3 bags of coal flat on your 2 feet. The likelihood is the bags of coal weigh more, and there's a greater amount of force being applied. But because it's not being applied at a singular point, it's not as painful. Okay, so pressure is a twofold system. It is the recognition that if you have a force that is spread out over some form of area, then that force, the effect of it, is less than the effect the force would have if it was concentrated at a single point. The best example of this I can give you is if you go and punch the wall if it's nearby, that's going to hurt. And no matter how hard you try and punch that wall, unless you've got really, really, really bad housing and you've got a plasterboard wall or something, you're not going to be able to put your hand through a brick wall. That's just not going to happen. But if you take a drawing pin and a very small amount of force with the end of a hammer, you're going to drive that pin in with very little effort whatsoever. Even though you're using less force, the effect is that you puncture the wall, and that is because of pressure. Okay, and pressure is defined as pressure, P-R-E-S-S-U-R-E, is equal to the amount of force that you apply divided by the area over which you apply that force. And we should have expected it divided by there, because we expect that as the area gets bigger, the effect of that force gets smaller. So you need to divide that force by numbers. Okay, if you get that area smaller and smaller and smaller and smaller and smaller and smaller and smaller, the effect gets bigger and bigger and bigger and bigger and bigger. Make the area bigger, the effect gets smaller. This is a feature of fractions, that as the bottom line gets bigger, the actual value gets smaller. So we've got this equation here, pressure equals force divided by area. So all you have to do is find the force, get it in newtons, and then divide it by the area. The big problem that people have with pressure is that you have to then get the unit. Now, force is non-negotiable. It's in newtons. End of story. Area, on the other hand, though, depends. Sometimes you'll have area in meters squared if you've got a reasonably large area. Sometimes you will have it in millimeters squared. if you've got a particularly small area, and if you've got somewhere in between, centimeters squared. And if you really go mental, you could have kilometers squared if you fancy, though that's not usually in a lab situation. So the unit that you end up with for pressure is simply the unit at the top per the unit at the bottom. So your options are either newtons per meter square, in the situation where the force is in newtons and the area is in meters squared, or newtons per millimeter squared, where your force is in newtons and your area was in millimeters squared, or newtons per centimeter squared, where your force was in newtons and your area was in centimeters squared. This is one of these nice situations actually where science doesn't demand that you use the standard units for it, though it is probably a good idea. Meters squared, however, being the standard unit, gets a special name. So the newton per meter squared is not generally given. We generally give it as PA for pascals, okay, in honor of the scientists who actually came up with this relationship. Okay, so newtons per meter squared tends to get rewritten as pascals, and you should rewrite it as pascals as well. The only difficult bit here is that perhaps in the exam, and I know I'm running over time here, but this is a useful little point, that perhaps in the exam you get given an area in centimeters squared and you have to turn it into meters squared because the exam demands the answer in pascals. Okay, so what we need to do is we need to be able to convert from meters squared, so we want to convert from meters squared, or from centimeters squared, say, to meters squared. Okay, so what I need to do is I need to draw two boxes, and do this at the side of your page or on a separate booklet. Draw two boxes that are identical to each other. Right? And the first box is 1 meter by 1 meter, giving it an area of 1 meter squared. The second box is identical but is measured in centimeters, giving you 100 centimeters by 100 centimeters, which gives you an area of 10,000 centimeters squared. I need to shrink that a bit because 10,000 is a big number. Okay, so what I can say is that 1 meter squared is exactly equal to 10,000 centimeters squared. So if I want to go from meters squared to centimeters squared, I'm going to need to do a little multiplication system here. So if I want to go from meters squared over to centimeters squared, my 1 has to become 10,000. And that requires a multiplication by a factor of 10,000. So going from meters squared to centimeters squared requires multiplication by 1,000. The opposite is also true. If I want to go from centimeters squared down to meters squared, then my scaling factor is going to be 10,000, but in the opposite direction. So we are going to divide by 10,000. This is a useful way of doing it. It also works for cubes. So if you want to know what 1 meter cubed is, draw a cube 1 meter by 1 meter by 1 meter, and then a cube 100 by 100 by 100, and you get the same game. It turns out to be 1,000,000 as the scaling factor. And then apply some common sense. If you're going from centimeters squared to meters squared, you would expect the number to get smaller. So once you've got the factor sorted out, you can apply some common sense. Right. Thank you so much for tuning in this evening. I know we're under a lot of exam pressure at the moment, so I appreciate you being here. That's us for the evening. 1 hour of good fun physics, everybody's favourite. Thank you again, and don't forget to hit the little like and subscribe buttons at the bottom if you haven't already, and I will see you in the next one. And don't forget everybody, physics rocks. It's true.